So let's summarize what we're doing before. We had this idea of span, right? From that span, we further introduced notion of basis, right? You see the difference? There's a spanning set, and here's a basis. What is the additional requirement? Linear independence. Excellent. And then I talked about existence of, and nobody cared about. There exists a basis, and then that's the thing. What was the other one? Uniqueness, right? The basis is not unique. You can come up with a different basis, but the uniqueness of a size of a basis, right? The size of that basis never changes if it is finitely generated. So that's so far what we have done. So from there we have this definition of a dimension of the vector space, n, right? What was the definition of a dimension of vector space? Right, number of vectors. And there's no uniqueness of the basis, therefore we had to justify it. What if somebody come up with a different basis? The numbers are the same, so this definition is all right. That's what we had done so far, right? So next thing is also very important. It's a very useful thing. I think they don't have a name, so I'd like to give all the names. I don't think it's a maybe it's a standard name. Base extension theorem. Basis extension theorem. I don't know. Got to give a name. So here it is. The idea is the following thing. So let's say I think this is. I think I'm going back to my notes again. About to change. There's this span there, right? No other condition is written. This is M. And then I'm calling this M. Okay. So from this condition, what is that I'm trying to say? Dimension of span of M vector is M. Then what's the conclusion? W through Wm is independent, linearly independent. If it's not, you can throw away one, then dimension will go down. So here's one mathematical way to say that this is the basis of a span. Is that all right? So we have this generator, the basis. If that's so, and then all this thing is inside some vector space in there, right? So with the dimension of vector space being n. So that's I have n vectors inside n vectors in there. So then I can, and there exist Wm plus 1 all the way up to Wn. You see where those things are coming from? Only m vectors, but we're going to extend it to n vectors, right? And so that the span of W1 through Wn now is going to be what? N. That's right. We've reached the full. So we have a small set of bases for subspace, and we can extend it to the big one, right? So this is called basis extension theorem. So the proof is not difficult, and I think it's something that we can definitely do together. So how does the proof goes? It could be the case that m is equal to n, right? We just happen to have m and sitting inside n. So it is a possibility that m is equal to n, then you don't have to extend anything. That's where to start, right? And if mn equals n, what do we say? So we're done. I never abbreviated before. It sounds weird. So what if not? What if not? And what if m is less than n? What is the step? Yeah, it's inductive, but I'd like to do it just one at a time. So what is the next thing we do? Well, let me look at this one. The span of W1 through Wm is not equal to V. Is that correct? If it is equal to V, why is it not equal to V? Anybody like to argue? Then m is going to be n, right? Because we already put that this is a basis. The logic clear? If equal, otherwise m is going to be n. So we said that m is less than n. So what does that mean? There's a thing outside this span, right? There's a thing outside. There's or one more vector, and that is not 0. And here's another thing. So there's lots of vector out there, and we're going to grab one, right? And which one are we grabbing? We have no idea. And some people have the problem with this type of description. And this is called axiom of choice. Some mathematicians like to be very clear about every action they're taking in mathematics. And so many of them out there, which one are you taking? I don't know, but there's one, so grab one. So that's the next step. What is that called then? There exists one vector, we're going to label it Wm plus 1, right? That is not inside that span of W1 through Wm. Does that make sense? What is the next thing we have to prove then? And claim, that's usually what they say, these m plus 1 vectors, right? What do we know about this guy? This is linearly independent. See if you can prove that. Why is this linearly independent? We know this guy is up to m is already linearly independent, right? So to check is linearly independent, what is that we have to test? The definition, right? If there's no other theorem. So we write it like this, W1. Let me emphasize it here. There's Wn in there, and n plus m plus 1, Wm plus 1 equals 0, correct? So how does it go from here? At this one and here, right? Consider, we hope that everything is going to be 0, right? So am plus 1, let's say if it is not 0, right? What's going to happen? What's going to happen if that's non-zero? Yeah, you divide by that vector. Eventually, you divide that scalar everywhere, and then what is the statement that we wanted to? It's not 7. It's not equal to 0. If that's not equal to 0, what statement do we want to pull out? Then it implies, if you move everything to the other side, it implies Wm plus 1 is a span of W1 through Wm. Is that right? So here, whatever that is, you can move it over here. After you divide it by the scalar, Wm plus 1 is inside the span. Any question about this thing? So let me do that. Wm plus 1 is a1 divided by am plus 1, which we can do because am plus 1 is non-zero. That's W1 on the other side, right? And do you see that? Oh, everything else is over there and showing that it's a span of that thing, right? Something that doesn't make sense here is a good sign, right? Why it doesn't make sense here? We chose Wm plus 1 outside the span. Yeah, right? So what is the conclusion then? Am plus 1 must be 0 because it's all started from that supposition. That implies Wm plus 1 inside the span, right? So contradiction, therefore conclusion, am plus 1 is 0. Once that is 0, then it is all about n vectors, right? We already know that's independent. Therefore, a1 through an is 0. So that argument you first gave is missing just that last bit. Okay? So if that's so, then we're looking at the statement W1 all the way through an, Wn plus 0 equals 0, right? Then why this whole thing is equal to an for what reason? Since why is a1 through an is all 0? Since W1 through Wn is linearly independent, right? That's how we started with. Remember that it's not n. Sorry about that. It's m. Maybe that's the confusion. M there. We started with m linearly independent. So if you're looking at that equation, everything has to be 0. Good? Yeah. Therefore, even all the way up to am plus 1 is a 0. That's the typical proof you see in the book. To going a little bit more carefully through with the definition. Maybe there is a different way to argue, but there is a danger of you fall into a circular reasoning if you use other theorems, right? So it's a part of a fundamental theorem as far as I know. All right. Well, that's only one vector we took care of. But don't you see that argument prevails just like that? Now you throw in 1. Okay, we have now W1 to Wn plus 1. See if that's equals to V, WAD. If not, then you throw in 1 more and argument goes exactly the same, right? So what do they say rest of the part? Blah, blah, blah. You know, the rest proof goes the same. Right? You're going to fill in carefully, though. I think we understood the idea. It's a fancier statement of this one. So here's a U is a subspace of V, right? This is not subset. This is a less than equal between vector space or subspace, all right? Subspace, then there exists W as a subspace of V, and U plus W is V. But better, this O plus, direct sum. Okay? That's kind of the same statement. And all done in provided if V is finitely generated. Because our argument is like one thing at a time, right? So that can be only done in this way. So argument extends to something called countable set of bases. It goes a bit trickier, but finite is just enough. All right. Do you see how the proof goes for this one? It's a corollary, so it's kind of the same idea. Some corollary uses the idea of the proof. Sometimes it's corollary just to use the statement. You don't have to go into the idea of the proof. Okay? Everything is happening in the finitely generated. Correct? So how is the first part of the proof? Is that U, we're going to write down U, right? U as a span of some vectors, right? W1 through Wm. Is that right? Good. What would be the W? Well, that would be, well, it's all right. W1 through Wm. How about now the statement is asserting the existence of subspace W. Does anybody know what that W is going to be? Wm plus 1, right. Through all the way to the rest of the part. So by theorem that we just looked at, exist Wm plus 1 all the way up to Wn, right? Such that this is linearly independent and spans everything, right? So that's, what is it? W span of W1 through all the way to Wn is V. Isn't that the statement before? You can extend that and then you can fill it up. Then let W be what? I think Chris said that already. What is the W is going to be? Span of something, right? Not that. B minus would be too big. Just want the generators. Idea is the same. This is whole generators. You subtract this generator, right? So in terms of generator, what's left? Wm plus 1, Wm plus 2, all the way up to Wn. Is that good? Yeah. So extension theorem says you have this many things, so just take the rest of the part and then create a W. It doesn't explain why we're doing that, but it's going to work, right? So that's the distasteful part about the modern mathematical exposition of the mathematical proof, that it doesn't share with you why we're doing this. It just works, right? But this is classroom period, and we talk about that. But sometimes the solution itself explains it. Now, what do we have to show now? First thing we have to show is that when you think about a direct sum, you have to always first think about this thing here, U plus W first, usual sum first, right? And it's supposed to be what? V. Let's see if this is obvious to you. U plus W. Span of that and span of that, it's going to be W. V here. Is that obvious? It's kind of obvious, right? So since of that statement, would that be all right? Well, you got everything, u plus w, right? And if you have everything, it's going to, w1 through wn is going to generate v. Cool? How about next one? What is that? We have to show my favorite one. What is the favorite condition that concludes this is a direct sum? Intersection. That's right. You have to show this intersection is a 0, correct? So I think Danny that did this problem in that homework problem. If you want to do intersection, you look at this element, that element, and set it equal to each other and see what you get, right? So what is it? How is this general element represented here? A1, W1. Anything is inside there is this guy here, right? Anything is in the U, right? So can that be anything over here? I'm going to use B1 Wn plus 1. So let me challenge you with a correct index here. What is a correct index? I think if you subtract these two, you get M. And that prevails all the time. So if you subtract, you're supposed to get M. So is that N minus M? Is that right? If you subtract these two, you get M. So I claim that index is N minus M. But that's not very important. It's just index in there. So what is this relationship between it here? Equal. This came from U, that came from W. Can this be equal? Right? It can be equal, and a possibility is that. So what do we do from here? A very simple argument here available. We organize it like this: W1 all the way up to AM WM minus B1 Wn plus 1 all the way up to minus Bn minus M Wn equals 0. I relabeled this right-hand side coefficient on purpose to give you a little difficult time to see what's going on. Okay? So what is the conclusion from here? But in this case we can. Why is that? What condition allows you to do that? Linearly independent. These n vectors are linearly independent, aren't they? Yes, we extended, right? W1 through that we extended so that it generates as a basis. And then every time when you throw in linearly independent, that was a fundamental thing that we checked. Therefore, everything is 0. What can that be? Then 0 equals 0. That element we're looking at must be 0 element, right? So intersection is 0. Correct? Okay. So does that prove that it's a finally that's a direct sum? Good. Any question? So that's I guess pretty much sums up the theoretical part when they introduce basis and dimension. And that theorem that I call fundamental theorem is, I think, is sitting at the bottom of an important trick. Everything else is fairly simple trick that you can easily understand and kind of keep it. But the other one was hard. All right, so that's that. We're returning to the sum and direct sum a little bit to give you a little more fun with this, what's happening with this direct sum here. So let's look at that. Here's a sum and direct sum. We just did that, right? All right, so here's fundamental theorem. Let me first, this is the important part that if you understand this one first, and you will see why it gets complicated and it's hard. So here, if you have two subspaces that trivially intersects, that was the term. And what was the conclusion about that again? That's good. That's absolutely right. What else? In terms of sum and direct sum, right? Yeah, this sum is a direct sum. Okay? If these two things are independent, I mean, trivially intersect, if you put it there, it becomes a direct sum, right? So here is best we can hope for if you have three subspaces is not intersection of a three thing. You can go a little stronger. All the mutual intersection is trivial. Isn't that a little stronger than all three intersections is 0, right? Even with these conditions, u1 to u2 plus u3 is not a direct sum. These are subspaces of V. Good question. Those are all U's. Here's a U. Is that what you're saying? And that everything is inside some subspace. You happen to be looking at three subspaces, and think about how they intersect. This mutually, they're trivially intersect. And then you can hope that these three sums of these three spaces, are they really direct sum, right? And then it's actually indeed is not. Okay? The sum of three vectors, the subspaces get weird, and there's no formula because of this phenomenon. But there's a neat thing about the two vector spaces. Okay? So let's look at this example. Let me first, when we write this two addition without parentheses, it means it's associative, right? Doesn't matter how you group it, the result is going to be the same. The meaning of this statement in here is actually the following. U1 intersection U2. I mean, U1 direct sum U2 with a direct sum of U3. If this is legit statement, and this must be true. So let's think about it here. That means U1 and U2 had no intersections, right? If it is a direct sum. How about this guy and U3? This one guarantees that U3 and U2 are trivial intersection, right? U3 and U1 trivial intersection, correct? That's when it's given. But the intersection of this whole thing and U3 is not trivial intersection. Can somebody explain that? This factors, the sum end here, trivially intersect with U3. But U3 may not trivially intersect with this entire sum. Sum creates more elements than what is in U2 and what is in U1, right? Sum creates more elements. Then this one doesn't say anything about what happened if you combine these two in there. Okay, here's an example. This is all taking place in xy plane. This is U1 passing through this origin. Does it look like a subspace? Right? How about this one? U2, does it look like a subspace passing through its 0? U3 is going to be like this. Often it's you enter, and that looks like XYZ space, but it's not. It's actually XY plane, right? Three lines passing through. Okay, so what about the mutual intersection? What do you see the mutual intersections here? U1, U3, what is mutual intersection? Trivial intersection there, right? You see that everything is a trivial intersection? But let's see, U1 plus U2, U1 plus U2. What is U1 plus U2? The whole plane. Is U3 trivial intersect U1 plus U2? No. Because U1 plus U2 generates a whole lot more than what's in U1 and U2. So this doesn't work. Okay, this naive condition that works in the kind of, you know the Venn diagram of the three sets putting together? Because two sets of union doesn't generate anything more than in this sum generate a whole lot more. It gets complicated. So there's no neat formula for this guy here if you intersect three of them. All right? But there is one, and this is the favorite item in the graduate qualification exam that explain this phenomenon here, because this one is very neat. All right, so that's that. So let me enter this decomposition, which I call this a theorem. And from there, we can deduce the theorem they're saying. So here is we have U1 and U2 as a subspace of V, and we call the U0 as intersection of these two. Only two things involved. And then, using that correlative extension theorem, I'm going to extend U1 as U0. You see that U0 is a subspace? U0 is a subspace of U1? Does that make sense? u0 is the intersection of that, right? So what can we do with that? We can extend that u0 inside u1 to new space. Is that right? So there is a complementary space. There's no unique choice to complementary space unless you have inner product space. You probably heard about inner product in first year course, right? Right now, we don't know. Lots of choices, just anything, you grab it. So why is this possible? What theorem? The basic extension theorem, correct? How about u2? u0 still sits inside as a common part, right? And intersection, the direct sum with u2 prime. Is this setup okay? This setup uses the extension theorem. Okay. Then what is u1 plus u2? We want u1 plus u2 as a direct sum expression so that we can calculate dimension nicely and we have things under control. Do you know the answer? There are things labeled in here. By looking at these two things added up, what is your guess? u1 prime? Yeah, u1 prime is in there. Oh. u1 is a space, and u0 is something inside a subspace, right? And then you can extend the basis to complete that from u1 to reach all the from u0 to reach all the u1. So that is this base extension theorem we just went through in here. If you're sitting inside some basis, some space, then you can extend it as a direct sum to make it complete. And there's no unique W that does it. Anything. So that's that any choice in here. And that's another complementary part of the choice. So example is that if this is u1 in R2, what is your u1 prime? And if this is u0, and if it is u1 is this whole place, what is your choice of u1 prime? Anything but that line, right? It's going to generate whole thing. And the intersection is 0. That's that. Okay? What if your u0 is this plane in three-dimensional space, and your u1 is R3? What is your choice of u1 prime? Any line that is sticking out. Together they will generate the entire space. If the u1 is a space line, u1 prime will be two other lines that is sticking out from that line, and they're not parallel to each other. What if the remaining basis is what this one is about? And it exists, correct? Because of base extension theorem. Now if you put them together, what happens is the following. u1 prime's there, u2, u0 prime is overlap, right? So you can just put u1, u0, and u2 prime. That's the direct sum expression. If you think about Venn diagram of just a set, makes perfect. If you just union of two things, middle part and the remaining part, and that gives the wrong, misleading idea towards what happens with the three spaces. Okay, so you shouldn't extend that because if the sum is not the same as union, that was the gist of the argument. All right. So here's a corollary to this one is the following. Dimension of u1, u2, right? Is the dimension of u1 prime dimension of u0 prime plus dimension of u2 prime. Don't you think that's true? Because that's all separated. Is one basis linearly independent to another basis if they're direct sum. So the first statement is that okay? But the second statement is called inclusion-exclusion principle in set theory. It holds just for the two sums. What's the inclusion-exclusion theory goes? Dimension of u1 plus dimension of u2. Then you know what to subtract out if it is a number of elements in the set? Two sets are here. Number of elements here, number of elements plus then you added too much in the middle, right? You subtract off what's in the middle. So dimension of what space? Intersection. u1 to u2. But it's not that simple. That's why you couldn't extend this inclusion-exclusion principle that works in the set to the vector space, and that was what this argument is about. Okay? Book in the exercises are going to ask you to give you some complicated formulation that is kind of suggested by this two-dimensional two-vector subspaces case, and ask you for the counterexample. And this is your counterexample. Apply the formula to these 3 lines inside R2, and you will discover the counterexample. Okay? And I'm going to challenge you with a more complicated example in the advanced problem. All right? It's not that if you look at echelon form long enough, and you'll find it in that advanced problem. But these are true statement. Okay, what is the wrong statement? Is that if I have 3 sums, you add 3, subtract of intersection of 2, and add it back, then it's this intersection with 3 thing, right? That statement is wrong, called inclusion-exclusion principle. Okay? All right, I couldn't do much, but